I'm Shravan. Uh, Welcome to DBS Talks. So, in power electronics, today our topic is operation of three-phase full control rectifier with R load and RL load. Okay, so three-phase. In last class, we discussed uh, single phase half control rectifier with R load, RL load, and RLE load. Oh, okay, and a pet of source inductance. But today we will discuss three phase full control rectifier with R and RL loads. So three phase full control rectifier is also known as full controlled bridge control rectifier. And here we are using 6 thyristors connected in the form of full wave bridge configuration. So all 6 thyristors are controlled switches which are turned on at the approximate times by applying suitable gate trigger signal. So the three-phase full converter is extremely used in industrial power application up to about 120 kilowatts output power levels. So where two quadrant operation is required. So here two quadrant operation is required. The figure shows the three-phase full control converter, the highly inductive load. The circuit also known as three-phase full wave bridge, three-phase full wave bridge or 6 pulse converter. So the thyristors are triggered at an interval of 30 degrees. So the frequency of output ripples voltage is 6 Fs and the filtering requirement is less than that of three-phase semi and half wave converter. Okay, so this is three-phase full wave control rectifier. Okay, this is the circuit diagram for three-phase full wave control, and it is also called 6 pulse converter. Why you call it 6 pulse means here we have six thyristors will be there. Yeah, and we are supplying three-phase supply. So T1, T3, T5. This group of thyristors are called positive group, positive group of thyristor, and T2, T6, T4. These are called as negative group of thyristor. Why it is called as positive means T1, T3, T5 will conduct for high voltages, and T2, T4, T6 will conduct for low voltages. So the thyristors T1, T3, T5 will be placed like this, and T2, T4, T6 will be placed like this, and here we are using load. So that is R load and RL load. Okay, starting T1, T2, T1, T2 will conduct, and T2, T3 will conduct, and T3 to T4 will conduct, and T4 to T5 will conduct, and T5 to T6 will conduct, and T6 to T1 will conduct. Okay. So this is a circuit diagram, and we have to triggered every thyristor with a firing angle 30 degrees, with a difference of 30 degrees. So at 5 by 6 plus alpha, thyristor is already conducting when the thyristor is turned on by applying a gate signal. So during the time period omega t equal to pi by 6 plus alpha to pi by 2 plus alpha, thyristors are conducted together and the line to line supply voltage appears across the load. Okay, so with pi by 2 plus alpha, the thyristor T2 is triggered and T6 is reverse biased. Okay, here before triggering, the T6 will be conducting, T6 will be conducted. When thyristor is triggered, then this T1 will be turned on, and thyristor T1 and T2 conducting together, and the line to line supply voltage appears. Thyristors are numbered in the circuit diagram corresponding to an order which is triggered. So the triggering sequence of the thyristor will be, so triggering sequence 1, 2, 2, 3, and 3, 4, and 4, 5, and 5, 6, 6, 1, and again the series will be repeated 1, 2, 2, 3. Okay, so the figure shows the waveforms of three-phase input supply voltage and output voltage of the thyristor current through T1 and T4, the supply current through the line A. So we define three line neutral voltages. So here we have neutral voltages VRN V. So here we are using three phase R Y B phases. So neutral voltages VRN VYN VBN, that is equal to VAN VBN VCN. So VAN equal to VM sin omega t, where Vm is the maximum voltage, and Vyn equal to Vbn equal to Vm sin omega t minus 2 pi by 3, and Vbn equal to Vcn equal to Vm sin of omega t minus 4 by 3. So corresponding line to line voltages are. So these are the neutral voltages, and line to line voltages VRY. So VAB equal to VAN minus VBN, and VYB equal to VBC, that is VBN minus VCN, and VBR, that implies VCA, that equal to VCN minus VAN. Here root 3 Vm sin omega t plus pi by 6, and root 3 Vm sin omega t minus 90 degrees, and root 3 Vm sin omega t plus 90 degrees. So to derive the expression of average output voltage of three-phase full-wave converter with highly inductive load, assuming the continuous and constant load current. The output voltage consists of 6 voltage pulse over a period of 2 pi radians. Hence, the average output voltage is calculated. Here, V average equal to here 6 pulse, 6 by, and it will conducting up to 2 pi. 6 by 2 pi into pi by 6 plus alpha to pi by 2 plus alpha Vm V naught d omega t. So V naught d, so V naught equal to VAB equal to root 3 Vm sin of omega t plus pi by 6. So by substituting 3 by pi into integral of pi by 6 plus alpha to pi by 2 plus alpha, that implies root 3 Vm sin omega t plus pi by 6 d omega t. That implies, by simplifying this, integration of sine means cos, cos, and substitute this limit pi by 6 plus alpha to pi by 2 plus alpha, then we get 3 root 3 Vm by pi cos alpha. That implies 3 Vm VML by pi cos alpha, and RMS voltage RMS value will be found VRMS equal to 6 by 2 pi pi by 6 plus alpha to pi by 2 plus alpha V naught square and d omega t whole power 1 by 2. So 6 by 2 pi pi by 6 plus alpha to pi by 2 plus alpha VAB square d of omega t whole power 1 by 2. So VAB means Vm sin of omega t plus pi by 6. So 3 by here 3 by pi, see integral of pi by 6 plus alpha to pi by 2 plus alpha, and 3 Vm square sin square omega t plus pi by 6 d omega t whole power 1 by 2. So by simplifying this, we get root 3 Vm of 1 by 2 plus 3 root 3 by 4 pi cos 2 alpha whole power 1 by 2. This is RMS value of single phase full wave control rectifier with R load. So we have to see the waveforms here at starting. This is the input voltage. So this is VAB and VA, VB and VC. These are the lines. At starting, T5 and T6 will be conducting. Whenever triggered will be given, then T6 will be T5 will be turned off and T6 will be turned off, and T5 will be reverse bias, and T5 will be turned off after T6, and T1 will be conducting, and T1 to T1 and T2 will conducting, and T2 to T3 will be conducting, and T3 to T4 will be conducting, and T4 to T5 and T5 to T6. Okay. So before triggering a gate pulse, the at starting T6 and T5 will be conducting. Okay, so this is the output voltage waveform we have to see. So VAN, VBN and VCN, there are three voltages will be there. So at pi by 6, the firing angle will starting. So at pi by 6 to uh, pi by 6 plus alpha and pi by 2 plus alpha and 3 pi by 2 and 2 pi. So here we have to see T6 will conducting pi by 6 to pi by 6 plus alpha to, okay, pi by 2 plus alpha. After pi by 6 plus alpha, T1 will conducting and at okay, so here we have to see BAB, VCB, VAB and VAC. Okay, this is VAC. After 270 degrees, T3 will be on. Okay, so we have to see T1, T3, T5 will be conducting in positive mode and T4, T2, T6 will be conducting in negative mode. So that's why T1, T3, T5 are called as positive group thyristors and T2, T4, T6 are called as a negative group of thyristor. So these are the continuous mode of voltages. So these are some some rippling will be here, some rippling will be there. So this is the output voltage at alpha equal to 30 degrees. So current, thyristor current, IT, IT3. So here from pi by 6 plus alpha to 5 pi by 6 plus alpha, IT1 current will be there and IT4 current will be 7 5 by 6 plus alpha to 7 5 by 6 plus alpha to uh, 7 5 by 6 plus alpha to 2 pi plus alpha will be there. Okay, so this is the current and output current will be continuous mode. Why? Because here three phase will be there and six thyristors will be there, so continuous mode of operation will be there. That's why the load current will be in continuous without any ripples. Okay, and next, operation of three phase full wave rectifier with RLE load. Okay, so the three phase full controlled converter is obtained by replacing all six diodes and of an uncontrolled converter by a sixth thyristor as shown in figure. Circuit diagram of three phase full wave control rectifier. Here we have to given a voltages VAN, VBN, VCN and to the input voltages and thyristor T1, T3, T5 and T2, T4, T6 RLE load will be there. Okay, and we have to see for any current flow in the load, at least one device from the top of your group T1 and T3, T5 and one of the bottom group T3, T4, T6 must conduct. So at starting, so bottom of one thyristor and top of one thyristor will must conduct. So it can be argued in the case of an uncontrolled conductor, only one device from these two groups will conduct. So then from symmetry consideration, it can be argued that each thyristor conduct for 120 degrees of input cycle. Now the thyristors are fired in the sequence T1, T2, T3, T4, T5, T6, T1 with 60 degrees interval between each firing. So therefore the thyristors on the same phase leg are fired at an interval of 180 degrees. So here these T1 and T4 will be fired with an interval of 180 degrees and hence can't be conducted simultaneously. This leaves only six possible conduction and mode of for the converter in the continuous conduction mode of operation. These are T1 and T2, T3, T2, T3, T3, T4, T4, T5, T5 to T6 and T6 to T1. Each conduction mode of 60 degrees duration appears in the sequence mentioned. So each of these line voltage can be associated with a with a firing thyristor with the help of conduction table. For example, thyristor T1 is fired at the end of T5 to T6 conduction interval. During this period of voltage across the T1 was vacated, and therefore T1 is fired at alpha. So angle after the positive going zero crossing of VAC, similar observation can be made about the other thyristors. So the figure shows the waveform. Different variables to arrive at a waveform is necessary to draw the conduction diagram, which shows the interval of conduction for each thyristor can be drawn with the help of phasor diagram if the converting firing angle of each thyristor will be given. So these are the waveforms will be there, and conduction waveforms also drawn. So angle after positive going uh, zero crossing of the line voltage with its firing is associated. Once a conduction diagram is done, all other voltage waveforms can be drawn from the line voltage waveform and from the conduction table. So similarly, line current can be drawn, output current of a conduction diagram. It is clear that waveforms that the output voltage and current waveforms are a periodic over the 1/6 of the input cycle. Therefore, this converter is also called a 6-pulse converter. The input current, on the other hand, continues only odd harmonic of input frequency of other than triplex. So the next section will analyze the operation of a converter. So here we have to say this is a conduction table, and it's a rectification. So three-phase full wave control rectifier in inversion mode. So this is rectifier and inversion mode. Okay, here at starting T6 will be conducting, after the T1, so T5 and T6 and T1. Here we have to see T1, T2, T1, T5. So T1, T3, T5 in positive direction, and T6, T2, T4 will be in negative direction. Okay, so this is a inversion mode of full control rectifier with a rectifier is inversion mode. So that's why the inversion mode output voltages will be like this. This is output voltage and this is conduction mode, and this is the inversion mode. Okay. So three input and output waveforms of three-phase full control rectifier in rectification mode. Here we have VAB, VAB and VBA and VCA output voltages will be there, and these are the T1, T3, T5 and T2, T4, T6 will be the conduction table. Output voltages will be like this, and the current output current will be in continuous mode of operation. Okay, here when you take a VT1 voltage at starting will be 0, and after that in inversion mode at 180 degrees it will be obtained, and here current input current will be like this. So this is the input and output waveforms of three-phase full control rectifier in rectification mode. So effect of source inductance in three-phase rectifier. So three-phase full control converter was analyzed with the ideal source with no interval impedance. When source is inductance is taken in account, the qualitative effect on the performance of converter is similar to that in case of single phase converter. Okay, so in finger shows such a converter. In case of single phase converter of the load is assumed highly inductive load. So when you taking a in source in inductance in a source, so the current will be flowing. These VA, VB and VC, here we are connected inductance, and this is a three-phase full control, full bridge control rectifier, and this is a load. So this is a circuit diagram with a source inductance of three-phase rectifier. So this is the waveforms. Waveforms for a three-phase rectifier with a source inductance. When taken VBC line. So when VBC line will be taken, it's starting here the source inductance, due to the source inductance, the current will be like this. So it will be formed from IB. So this is IB. When taken one line, so IB at pi by 2, it will comes to 0. After with some angle, it will be starting and it will be conducting up to 3 pi by 2. So here these are the overlap angles. At starting, T6 will be conducting, after that T1, and after that T2, and T3, T4, T5, T6. These are the conduction mode of operation, and waveforms output voltage V0 will be like this. So it will be forming rippling. Okay, so continuous mode. Why? Because this is a 6 pulse converter. So as in case of single phase converter commutation are not a instantaneous due to the presence of source inductance. It takes a place one overlap period of mu1 instead of during the overlap period of 3. Thyristor instead of 2 conducts. Current in the outgoing thyristor is gradually decreases to 0 while the incoming thyristor current increases and equals to total load current. At the end of overlap period, if the duration of the overlap period is greater than 60 degrees, 4 thyristors may also conduct, clamping the output voltage to 0 for some time. However, this situation is not very common and will not be discussed any further in this lesson due to conduction of two devices during commutation either from top group or bottom group instantaneous output voltage. So during the overlap period, so when you have to derive this hatched portion, so resulting the reduced average voltage, the exact amount of this reduction can be calculated. So in the time interval alpha less than omega t less than alpha plus mu. So T and T from the bottom group, T and the top group conduct. So 6 to 1. So the equivalent circuit of a converter during this period is given. So when thyristor T6, T2, T1 will be connecting. So the equivalent circuit of waveform of source inductance. Here VA, source inductance, and the current YA, it will be goes in source inductance VB and VC and IC. Okay. So this is the equivalent circuit when it will be conducting with a source inductance. So when you derive the equation for source inductance, therefore in the interval alpha less than omega t less than equal to alpha plus mu, VB equal to L into di by dt minus L into dic by dt plus Vc. So from this diagram we have to write L into di by, so VB equal to, here VB equal to L into di by dt minus L into dic by dt. That implies minus L into dic by dt plus Vc, and VBC equal to L into di by dt of IB minus IC. But IB plus IC plus I naught IA equal to 0. So dIB by dt equal to minus of dic by dt. So 2L into di by dt of IB equal to VBC equal to root 2 VL sin omega t. IB equal to C minus of root 2 VL by 2 omega L and cos omega t. At omega t equal to alpha, IB equal to minus I naught. Therefore, C equal to root 2 VL by 2 omega L cos alpha minus I naught. IB equal to root 2 VL by 2 omega L cos alpha minus cos omega t minus I naught. At omega t equal to alpha plus mu, IB equal to 0. So, and therefore, root 2 VL by 2 omega L cos alpha minus cos of alpha plus mu equal to I naught. So, by simplifying this, cos alpha minus of cos of alpha plus mu equal to root 2 omega L by VL into I naught. So for mu less than or equal to 60 degrees, it can be shown that where it is a condition to be satisfied. So I naught is less than or equal to VL by root 2 omega L cos of alpha minus pi by 3. So to calculate the DC voltage for alpha less than or equal to omega t less than or equal to alpha plus mu, V naught equal to VA minus VB plus L into DIB by dt. That implies 3 by 2 VA. So for alpha plus mu less than or equal to omega t less than or equal to alpha plus pi by 3, V naught equal to VAC. So by substituting this V naught equal to 3 by pi integral of alpha to alpha plus mu 3 by 2 VA d omega t plus alpha to alpha plus pi same alpha plus pi by 3 VAC d omega t and 3 by pi alpha to alpha plus mu VAC plus 3 by 2 VA minus VAC plus alpha plus mu to alpha plus pi by 3 VAC d omega t. So by simplifying it, we get 3 root 2 by 5 VL cos alpha minus 3 by 2 pi alpha to alpha plus mu VBC d omega t. So R V naught equal to 3 root 2 by 5 VL cos alpha minus 3 root 2 VL by 2 pi integral 0 to alpha plus mu sin of d omega t. So 3 root 2 by 5 VL cos alpha minus 3 root 2 VL by 2 5 cos alpha minus of cos of alpha plus mu. That implies V average equal to 3 root 2 by pi VL cos alpha minus 3 by pi omega L I naught. So for source inductance in three-phase full wave bridge rectifier, average voltage will be this, that is, and that's it. So thank you.